Okay, welcome everybody. So this is the second lecture in the series of two talks by Professor MALABIKA Pramanik. Well, she'll continue her talk on distance sets today as well. Let me also take this opportunity to publicize the public lecture she will be giving tomorrow at the planetarium at 4 o'clock. So,
Thank you, Naru. So, as promised, I'm going to continue our discussion from yesterday about distance sets with a focus today on the continuum version. So, just a quick reminder, given a set E, the distance set of E is simply the collection of non-negative numbers, absolute value of x minus 1 as x and y range over E. There is this one motto that underpins this entire lecture. Large sets have large distance sets, and that's what I'm going to keep coming back to in the continuum setting today. Okay, so one of the things that you realize very early on in this business is how many different types of results under the umbrella of distances there are. And it's very easy to get confused by the conditions, by the assumptions, and by the conclusions. So I was trying to figure out a method in this madness that I could convey to you. So I'll give it a try, and you can tell me later on if this worked or not. So I'm going to, on this board, I'm going to talk about maybe the properties of delta E given size of E. So I'm going to just, this board I'm going to just delegate to the different types of properties. Then this one will be a discussion of Lebesgue positive sets. And over here, we are going to try and work on the sparse version. So I hope this will sort of allow you to kind of follow the different threads of thought. At least that's the hope anyway. Okay. So what is the first property? So the first property, number 1, it's about intervals in the distance set containing the origin. That's property number 1. Okay? So if that is the property, how exactly is this being achieved? So here's the result corresponding to 1. When I say Lebesgue, what I really mean is I'm going to look at subsets E of Rd whose d-dimensional Lebesgue measure lambda sub d is positive. Okay? So with that assumption, I told you yesterday about this old result of Steinhaus. From way back when, the conclusion says that if that's your setup, then this implies there exists some positive A such that delta of E contains zip to it. Okay. What about the sparse version? What do I mean by a sparse version? Well, sparse version means that it's Lebesgue null. So we'll be talking about E the d-dimensional Lebesgue measure is 0. But the Hausdorff dimension, we also talked about this yesterday a little bit, and I'll remind you again today. It's another marker of size. This is strictly smaller than d. In this case, question is, do we have such a statement that involving intervals in delta E? The answer is no. No such result is. It's not that it's not known. This result is known to be false in this generality. Okay, so at least is the idea clear what I'm trying to do? I'll state a property. I'll state what is known in the Lebesgue case, and then try to analyze what we know about it currently in the sparse case. Okay. All right. What's the next one? This one we kind of touched upon a little bit. So uniformity in delta E as E ranges over a large class of sets. So what does that mean? That means that these are statements which hold for every different A, but we kind of want some uniformity in the parameters so that the many different sets E will somehow conform to the same value of A. So this I kind of briefly touched upon yesterday, and we shared a little simple proof together. This is due to Boardman. So from 1970. And yesterday we talked about the dimension 1 version. Today I'll state the more general statement. So let rho be a small constant. So maybe we should say there exists a small constant rho, which depends on D. And when D equals 1, yesterday rho D was a half. So there exists a rho D with the following property. For every E Borel subset of the unit D-dimensional cube, with Lebesgue measure larger than 1 minus rho D, the distance set of E contains an interval 0 to C sub D, which depends only on the dimension. So this is a uniform constant, which works for all E with this property. Okay? Any questions so far? Yes.
Maybe you said yesterday, but I've forgotten.
Yes.
These rho Ds have been studied as D change.
As the dimension changes? Well, yes. In the case of the only satisfactory result is when D is equal to 1, where it is known that if rho D is equal to a half, then the CD, there is a formula for this in dimension 1. And if rho D is larger than a half, it is known that this CD is 0. For higher dimensions, this statement, as I have written it, is known, and a quantitative bound on rho D is known in the sense, for example, if it is like half to the D over D factorial or something like that, then this result is known to be true with an explicit constant for this. It is not known whether that rho D that I just mentioned is sharp or not. Okay. All right. Now, what exactly is the sparse version of such a uniformity statement? And that's what brings me to this result that the first result in this direction was our joint work with Rani, who's in the audience. Okay. So I want to write down first what this sparse version is, why it falls in category 2, and then what are all the different other things that it implies. Okay. So we want to say that this is, we call this a uniform Steinhaus-like theorem. So I better be clear what I mean. So this is for d larger than or equal to 2. There, we needed a row. Here we are going to need two-dimensional constants, rho and epsilon, both of which are smaller than 1. And they have the following property. Take any E subset of 0, 1 to the d, okay, whose d-dimensional Hausdorff content, and I know I have to explain this, what this means to you, is large. So this is the size condition. This is a large set for some rho below this threshold and some S that is bigger than d minus epsilon. Okay. Then what's the conclusion? The conclusion is that delta E contains an interval A sub rho, B sub rho, where these two numbers, A and B, these are constants depending only on rho and on nothing else. A, B depend only on rho and not on. Okay. So let me, it's easy to get lost in this jungle of different types of notation. So it's probably a good idea if I'm trying to explain to you what the new additions to this result are. First of all, since we have to go below Lebesgue, we have to make sure that our sets have large Hausdorff dimension. This is the quantification of largeness, and I should explain to you what this HS infinity means. So what is HS? This is called the S-dimensional Hausdorff content of E. It's a measure of size. So how is this size being measured? I gave you an inkling yesterday. So start with any countable cover of E by balls. So this ball is, let's say, centered at xi and the radius ri. And for this countable cover, you create the sum ri to the power of s. Okay? You run through all the different covers and you take the infimum of this object. So if this number is large, the way you should interpret this condition, by the way, just to sort of get our head straight, what is the S-dimensional Hausdorff content of the cube, of the unit cube? And if it helps, these are equivalent statements. Maybe we should make our life easier. Instead of balls, can we let's do cubes themselves. So let's call it QXI RI, where QXI RI is my notation for a cube whose left endpoint is xi, and then that's a cube. So what is the S-dimensional Hausdorff content of the unit cube? Okay, at the risk of offending you, what is the one-dimensional Hausdorff content of the unit cube? Yes, that's okay. So what is the number? 1 to the IS. And you should check that if you take any smaller Ri, the sum will exceed 1 because S is smaller than D. Okay? So Hausdorff content of the unit cube is 1. And you should compare this. This condition just means that if you have a subset E of the unit cube, the S-dimensional Hausdorff content of E really comes real close to filling up the content of the unit cube. This is the largeness assumption. So this quantifies the largeness of E.
This case though, because 1 power everything is 1, the S less than D was not actually.
No, but it's this is always true. In fact, for any E subset of 1 to the D, everything is less than or equal to 1.
0, 1.
Yes, but then you also have to show that this is the infimum, right? Okay. All right. So then, this is the largeness of E, and large sets have large distance sets. So this is the uniform largeness of the distance set. Okay. So that's one comment. The second comment is that unlike Boardman's result, where the interval was 0 to C sub D, this constant A sub rho is definitely positive for us. And it's positive not because we couldn't prove this to be 0, it's positive because it is known that this cannot be 0. There are lots of Lebesgue-Null full dimensional sets which do not contain any interval around the origin. So if such a result were to be true, if such a uniform Boardman-like theorem were to be true, this number, the lower bound, has to be away from 0. So A sub rho is positive and this is required. Okay. So this is a big difference between this and this. Now, what I want to do, then this in fact was kind of surprising to us, was how one type of result in distance sets actually cascade into a whole slew of other results, also in distance sets, but of a very different flavor. And I want to use this result as a springboard to tell you about all the other ramifications that it can generate. Okay? Yes.
So the overall overarching thing was that E is null, but the exact example you took of the actual unit cube is certainly not enough.
No. This was an example of Hausdorff content that I was still trying to tell you about. So, but I think it may also be a very good idea to keep in mind an example of a truly sparse set, or at least an iterative construction of a sparse set. So, suppose you have, this is your unit cube, and you generate a lattice in it, okay? And to each lattice point, you attach a little thickened cube. So your E, this could be the first iteration of your sparse set, okay? So it is sets like this that's of interest. The reason I talked to you about the unit cube was to identify where this 1 came from. This 1 is really H infinity S of 0, 1 to the D. So that's what it means for E to be large. That was the reason. Okay, great. Any other questions? Okay. All right. So we are going to keep talking about different properties of distance sets. This was uniformity. What's my next property? Let me see. So yes, please, by all means.
When this is sort of full, you have 1 is that thing.
Yes.
So even for very small positive rho, you do get 0 measure things with HE bigger than 1 and so for very small.
So you want?
I'm asking about the existence of such E for arbitrarily small rho.
So are you? So S is S less than
S
D?
is less than.
S is less than D. Oh, absolutely. You can definitely have sets where H of S of E is actually equal to 1. Right. Okay.
Null sets.
Null sets, absolutely, null sets. Okay. So, number 3. The next thing that I want to talk about is something called a Matila-Sholin theorem. And in fact, this has the property that it's going to be talking about is types of intervals, topological structure. This is number 3. And because I'm running out of space, what I'm going to do is I'm going to erase the top and put number 3 here. And that yes, please.
Depending on how you produce such a rho D.
So you're asking me how the proof works?
Well, maybe not in entire detail.
Right,
If
right.
it can be done. Yes.
Okay.
Just because it seems quite surprising. That's why.
Yes. Okay. I could try to. I'm trying to. I'm trying to rack my head for like a 2 or 3 line explanation, which will at least give you a flavor from where this this rho sub d and epsilon sub d come from.
Yeah, because that was constructed more or less.
This result?
Yeah. Which you explained yesterday.
Yes. Okay. So the way we do this, the short answer is, suppose that we have an E such as this with the property that the Hausdorff content is large. So that's all we have, okay? Our job is to construct a measure on this E so that, the way the measure is going to be constructed is as follows. So let me try drawing something here. So this is E, the unit cube where E lives. So there are, I'm going to sort of draw some blobs, and these blobby parts are the E's, okay? The first thing I need to do is, all I know is this content condition, And using this content condition, what I first do is go through a dyadic decomposition of 0, 1 to the d, and we pick out certain dyadic cubes where the E holds large weight. Okay. Once E holds large weight, what I want to do in order to determine the distance set, what I want to do is I now, depending on these special measures, I want to create something called a configuration integral. What does a configuration integral do? Given a measure, it tries to pinpoint the distance set in that measure, the support of that measure. So it's an analytical function. It is, for example, an example I could give to you is like this. So let's look at this integral, f of x plus t omega d sigma omega dx. So this is an integral. And this sigma is actually the unit sphere, and x is, let's say, supported on some set E. Do you see that this is an integral? And the positivity of this integral tells you that there is actually a distance of t inside E. This is my main tool. A configuration integral like this is my main tool, except that, of course, my sets are sparse, so we don't have actual functions, we have measures. So we construct measures on the set E based on this property, for which we can show that such thing is positive, and proving the existence and positivity of such an integral requires us to be as close to Lebesgue as possible, and that brings in these thresholds. Okay, so I'm trying to summarize it in as transparent a way as possible. Let me give it one more try. Our goal is to identify that these points in this interval, the t belongs here. For every t inside this a, b interval, I want to show that an integral like this is positive. That will show that the point t belongs to the distance set. In order to show that that is the case, I need to find a function defined on the set E. This would have been possible if E was a positive Lebesgue measured set. It is not, it is Lebesgue null. Therefore, such f's may not exist, but measures supported on E exist, and we show that that's positive. Okay. All right, so where do we go now? I'm going to, yes, I'm in 3, and I was going to put the 3 here. Let me give this a try. Okay. So there are topological structures here, but I'm not going to, this will take us too far afield. I want to sort of keep to our program here, so I'll just go directly to the sparse setting and tell you about a really famous result called, well, yesterday I told you about the Falconer's distance set conjecture, so I might as well say this here. So this is Falconer. And what it said is, suppose that D is bigger than or equal to 2. If the Hausdorff dimension of E is strictly larger than half of the ambient dimension, then the one-dimensional Lebesgue measure of the distance set E is positive. And I told you yesterday why it's still a notoriously difficult open problem, but a lot of work has been done on it. Now, even though Falconer's distance set problem remains open, there has been a lot of similar questions of similar flavor, which I'm going to call as 3', which are not conjectures, but actually theorems. So This is a result of Matila and Sholin, and I think from the late 80s, 86 maybe. Okay? And what they showed is that if the Hausdorff dimension of E is strictly larger than d plus 1 over 2, so you realize stronger condition than this, then delta E has non-empty interior. So stronger assumption and stronger conclusion. It's related to Falconer, but obviously not Falconer itself. Okay. All right. What was not known is, once again, this is a qualitative statement. This is like Steinhaus for some AB positive. And we have no idea how to quantify, at least Matila and Sholin's result does not give us any way to quantify what this A and B might be. Okay? It was surprising to us that as a result of this uniform Steinhaus-like theorem that we obtained, we could actually specify exactly what these intervals are. And that's what I want. So I told you today that today's talk is going to be about a network of connections. This is the first one. That uniform Steinhaus-like theorem actually gives rise to a quantitative Matila-Sholin theorem. So let me state that first. I don't want to give up on this just yet, but maybe what do I mean? So let's talk about this. So our quantitative Steinhaus implies quantitative Matila-Sholin. So let me identify what this is, and this is also this is just part of our work with Rani. So it says the following. So suppose you have dimension. There are certain places where our result will fall short, and you will see it soon enough. So suppose that this is larger than d minus epsilon t. So remember our earlier result had a rho sub d and an epsilon sub d. Okay. Then delta of E contains actually a union of intervals A rho and B rho. These numbers come from the previous result, multiplied by a certain and the only way to make sense of this is if I draw a picture. So I'm going to do that in a moment. So this is the union over all such cubes. So here is the picture. This is 0, 1 cross 0, 1. We are going to look at certain cubes. So they are not all of the same size, however. So let's say you pick this cube. None of these cubes are picked. So over here, this one is picked. And these shaded dyadic cubes are being thrown into a pot called D rho. Okay, so I'm going to define what the defining condition is for D sub rho. So D sub rho this is the collection of all cubes Q, so these are the cubes Q, all the dyadic cubes Q, and the left-hand endpoint of the cube is called the C of Q, and the length of the cube is called L of Q. And what are these dyadic cubes being chosen based on? Such that when you look at the S-dimensional Hausdorff content of E intersected with Q, that exceeds 1 minus rho times the length of Q to the S. Okay. So let's try to kind of sit back and take a look at what this is trying to say. It's a lot of notation, but I promise there is a method to this madness. Okay. You should think of this D rho E as high density cubes. Remember that capital E is a sparse set. Its points are kind of distributed in some haphazard manner and in a way so that the Lebesgue content is null. We have to find a way to kind of grasp where the points in E lie and how thick are they. So the way we do this is we start with the full interval, the full cube 0 to 1, and we look at its first generation children. On the plane there are only 4 children. We ask for each of the children, is this defining condition satisfied? So when we look at the proportion of E inside one of these children, does it exceed at least 1 minus rho times LQ to the power of S? This is the S-dimensional Hausdorff content of this cube. So does E occupy a large proportion of this child in this sense? Okay. If the answer is yes, you pick it. Otherwise, you don't pick it and you keep going. If something, for example, this was not picked, as you can see, if this is not picked, we split again. And for each of the descendants, we ask the same question. Does E occupy a large proportion of this dyadic cube? If yes, keep it and set it aside. You don't have to come back to it again. If not, then you keep splitting again. So it's like a stopping time argument where there is a criterion of largeness that determines which cubes you choose and which cubes you throw. Okay. Usually at this stage, I wait, and there is a question, a very natural question, which I'm expecting somebody will ask. What is that question?
You aren't repeating it.
Sorry, it was an observation, but go ahead nonetheless.
You aren't repeating cubes.
I'm not repeating cubes because once you see this cube was picked, once this cube is picked, I'm not splitting it anymore, right? So space is not being overcounted. Yes. Thank you. Yes, I could split away to glory, and if every single time this fails, then at the end of the day, my collection of cubes is empty, in which case the statement of my theorem would be vacuous, right? That was the point. So if this result were to hold water at all, I had better show that my largeness condition that I began with in my theorem, this largeness condition, it at least gives me that the non-emptiness of this collection, right? Okay, so that's what I'm going to do here. So Y is d rho of E see if we can at least put one proof on the board why this should be the case. Okay. What do we know? What we know is that the S-dimensional Hausdorff content, whoops, my S and infinity, of E is positive. Why do we know this? This is actually a standard implication of the fact that the Hausdorff dimension of E is larger than this. Okay? So this we know that the set, this is where we started, right? This was our assumption. Let's say this is my S. All right. What does that mean? So that implies, so let's give this a name. Let's call this H. And if you remember, the Hausdorff content was supposed to be coming out of coverings. So that means that there exists a cover Qi with some center and some side length Ri of E such that when we look at the sum Ri, or maybe I should call this Li for length. This is, by the way, just my standard notation I think I told you before. When you look at summation Li to the power of S, this comes arbitrarily close. So this would be the infimum of all such things. So Li to the power of S would be less than H times plus an epsilon. Do you know where this statement came from? Why is this true? I'm just checking if yours. Why is this result? Where does this cover come from? That's from the definition. That's exactly right. So it's the definition of a covering. In fact, for any epsilon, this follows from the infimum. So in fact, what I'm going to do is I'm going to write this as 1 plus some epsilon. For any epsilon, this should be true. Questions? Okay. All right. Now, here is where what I'm going to claim is that at least one of these cubes must lie in this collection D sub rho. And that would show that the collection is non-empty. So the claim is, at least one Qi belongs to this. Okay. Why is that? Suppose not. So if the claim is false, then let's see what we can say. We'll start with the S-dimensional Hausdorff content of E. By triangle inequality, we will just bound it by the cover E intersected with Qi. And if we assume that D rho was empty, that's the contradiction that we are trying to get to. If every single Qi failed to have this defining property, that means that the opposite inequality must be true. So that means that this should be less than 1 minus rho times the sum of Li to the power of S, right? Do you see the contradiction yet? Summation Li to the power of S was chosen to be less than H times 1 plus epsilon. This is from here. And this times 1 minus rho. Any contradiction yet? If you choose epsilon to be equal to rho, it would end up showing that 1 less than 1 minus rho squared, and that would be a contradiction. So this collection is always non-empty. This statement always makes sense. All right. Let me see if there are any questions. If not, I might say a couple more things before I end. Yes.
Maybe not following something.
Yes.
I can figure that is a cube.
Yes.
Why should it be such a dyadic cube? Like why should it come up with this process of biting?
So this is a very valid question. So there are a couple different ways of answering this. When one looks at, so there are different objects. One is S-dimensional Hausdorff measure. The other one is S-dimensional Hausdorff content. And whenever you define these, you can choose to go one of two ways. There are many equivalent ways of defining this. You can use balls to cover. You can use cubes. You can use dyadic cubes. Now, these definitions are not identical in the sense that the value of HS infinity that you are going to get from one will not be the same as the value that you will get from the other. However, positivity and finiteness are preserved. So it's an important result, fundamental result. You can look it up in Perty Matila's textbook, that if HS infinity is positive using dyadic covers, that is equivalent to the positivity of this object using just plain cube covers without dyadicity. Any other questions? Okay, so there is one last result that I want to end with. This is still, so I talked about quantitative Steinhaus implying quantitative Matila, and I still want to keep on like pushing that network of connections a little bit, simply because it touches on a result that I really love, and it lets me come back to this Lebesgue's concept, which is to talk about all sufficiently large distances. So this is the fourth property that I should have put there, but I have already kind of lost that game, so I'll put it here. What does this say? So here the notion of largeness is something different. So the assumption is that E subset of RD has positive upper density, which means the following. Take E and put a real, okay, let's keep everything simple. So let's just truncate E into a large square and ask what proportion of the square, maybe I was using lambda d, so let's do that. What proportion of this square is being covered by E? And let's take the lim sup as R goes to infinity. Okay? So this object is called the asymptotic density of E, and let's assume that that's positive. Yes, yes, yes.
So in Matila-Sholin, this A can be very close to 0?
A can be very close to 0, but it cannot be equal to 0. Yeah. So again, this goes back to a construction which shows that there is a set of full dimension equal to D for which delta E doesn't contain any interval of the form 0 to A. Okay, so assume that E is a subset of RD with this property, D is greater than or equal to 2. What does all sufficiently large distances mean? It means that you can find an M such that the distance set contains a half line. Every real number larger than or equal to M is actually realized as a distance of E. So when we say large sets implies large distance set, this is yet another rendition of that same phenomenon. Largeness now means positive asymptotic density, and largeness of the distance set means the containment of an infinite half-line. Okay. It is also known that trivial relaxations of this condition, so this is actually a result by many people independently and concurrently. So this is due to Furstenberg, Katznelson, and Weiss. They gave a proof using ergodic theory. A harmonic analysis proof is due to Bourgain, and a proof using geometric measure theory is by Falconer and Marstrand, all roughly at the same time and using different proofs. It is also known that trivial relaxations of this condition is not possible. Many counterexamples exist. One of these are network of connections from the quantitative Matila-Sholin that we obtained in our work with Rani is that such a statement actually, if appropriately souped up, gives rise to a notion of distribution, a notion of well-distributed sparse sets such that delta E contains all sufficiently large distances. Okay, so if I had more time, I would have shown you also. It's not terribly difficult, but it will take me more than 5 minutes, so I won't belabor that point. But maybe I should just end on the note that distance sets, that area is vast. It is vast, it is vibrant, it's multifaceted, and the number of ideas, methodologies, and tools just defies imagination. What is still being thrashed out is even within this arena, one notion of largeness of distances actually implies many other notions of largeness and properties of distance sets. So my hope in today's talk, which I think I deliberately made more technical than yesterday's, was to give you a flavoring of this web of connections. And I hope that if you find this interesting, you will go and look up some of the other incredibly rich results that I didn't have time for. Thank you so much.
So the M you have given,
Yes.
so that is only dependent. So like, do you know the dependencies?
That's the exactly right question to ask. Right now, this M depends on E. And in fact, there are many examples where this could be, I think, so this could be delta. But as far as I know, this M does not depend on delta alone. There could be many sets with the same delta, but this M varies. Okay? It would be really interesting to get a uniform version to see what that might look like. I'm confident that part is not known.
Any other questions?
Yes.
Here the result was L2 times A.
Yes, I'm going to write it just so that, yeah. So delta E, so you are looking about the quantitative Matila-Sholin, right? So LQ, A and B, yeah. Yeah.
When the cubes become smaller, they should become higher density. Assuming that data set.
So as you go smaller and smaller, at some small level, so even if it fails at a certain large level, on some tiny level, you will have high density cubes. The moment you hit the first high density cube, you stop. Because
The next one will not be. Okay, you have already picked that.
Yes, I have already picked it, and I don't look at its further children anymore. There is a reason for this. You see, you can go on splitting away, and chances are if you keep going splitting away, if this has positive dimension and so on, it will still give you more children. But let's see what's the point here. The point was to identify large intervals inside the distance set. As you go to like smaller and like more and more like down the line of ancestry, this LQ becomes smaller and smaller. The intervals having tiny intervals which are probably already subsumed previously doesn't help. So the goal is to see the moment you win, you stop so that you have the largest LQ subject to that defining condition. If you don't,
So then maybe I got confused. So LQ times A row B row is just a multiplication, right?
yes,
But so when LQ becomes smaller and smaller, your left hand point is going to 0.
it's left, it could go to 0, but then we don't know how the, I mean, it is also true that if you keep going doesn't mean all the descendants are going to have the same property. It is not true that if one Q obeys the defining condition that all its children obey that defining condition. That's not true.